Okay, hello everybody. Today we'll talk about shaders, which are actually small programs that you can write and run on the GPU, right? So the GPU like do all these things, magic things that we have seen, like transforming vertices from one reference frame to another, computing lighting and stuff like that. So what you actually can like trying to extrapolate from that is the fact that GPU, and we also discussed it last time, it's a very efficient, highly parallel computational device that it's possibly to use as a generic programming, like a generic processing unit, or you can program it to get the desired effect. So those are shaders. So let's try to recap a bit what we have done so far last lecture. So, um, so we have seen that actually the architecture of the GPU is significantly different from the CPU. So the CPU, what you want to have is something which is a bit more generic, so that you can write your program, compile and run it. And of course, you have some degrees of parallelism, but most of the uh, actually components they have to handle like the control and the synchronization between the different arithmetic logic unit, right? And of course you have the cache that is shared between all the arithmetic logic unit. But on other hands, the GPU instead it's massively parallel, so you have a lot of small processing unit which few control hardware, and the control is demanded to the user, right? But if you can write a nice program, right, if you can write an efficient program, it becomes a very uh, powerful tool for computation. So we have seen that a bit about the pipeline, and now it will be interesting the fact that we can actually go more in deep and program this pipeline with the shaders. Right? I'll show you the example, and shaders are not mandatory for the project, right? But of course, they will be in the quiz. Okay. Uh, if you add the shaders, that's fine. If you go out and go work for some company that do like animation, that do like rendering, if you can write a shader, that's a big plus. Okay. For example, if you go to Animal Logic, you go to Pixar, you go to work at Disney Animation Studios. So yeah, they really are interested in people that can write shaders because it's not easy, right? Even though there are a lot of shaders around that you can get, but it's a very specific skill. So, okay, so the pipeline we have seen so far. So you put a vertex, right? You put a triangle with a set of vertices, which are expressed in object coordinates, which are the coordinates the modeler uses to create its shape. As you have seen, when you actually import some mesh in 3JS, this mesh can be everywhere in the space, right? Then you apply some transformation to these coordinates, and then becomes world coordinates. Usually this transformation is bring the object in front of the camera. This is the basic one, right? But you can even apply something more complicated. Then there is a sorry, this V and M, they should so this one should be M and this one should be V. Okay, so I will correct later on. And then you have the view matrix that transform world coordinates to view coordinates. And then you project, you have the clip coordinates depending about the kind of projection. And then you have you put back to the screen space, right? So so in the end you have the viewport matrix that transform the clip coordinates right to the screen space. So, and we have seen that actually within this pipeline there is 9 degrees of parallelism, which means like all these vertex in this stage, they are processed in parallel, and all the pixel in this stage, right, are processed in parallel. Okay, so to derive the color for the pixel or to derive the shading, in case you do found shading, right? For example, or for example, algorithm such as the rasterization, right? It's processed in parallel. So rasterization happens before, as we have seen, it happens here, right? So you actually try to understand when you have a triangle in screen coordinates, right? So which pixel you have to turn on and off for the triangle on the screen. We have seen that in the last lecture. I'm trying to make a recap, so I'm going quickly. So the idea is how we do that. You compute the bounding box, so which is axis aligned box containing this triangle, and then you start like sampling points and seeing when the points are inside or outside, and you group the points in groups of 4 or 8 pixels, right? Not points, which are called also fragment, because it's a pixel with some more information we'll see later. And then once you have something that falls outside, that's everything is outside, right? And do the same for every line. So in this way you can actually understand which pixel to illuminate for on the screen for your triangle, right? And consider that for each one of these pixels, we'll see now, you have one small program called fragment shader, right? So you have one vertex shader for each vertex, one fragment shader for each pixel, right? We have seen also the backface sculling, so the fact that you can actually discard the face whose normal is the same direction of the viewpoint. That means that the face you are looking from the inside, right? And you discard a lot of face, and you actually discard the elements from this point of view on, right? So that means that you actually don't have even to compute the, I mean, you don't generate any fragments for that. You discard them directly with the geometry, because, I mean, if you have a triangle, if you have the point of view, you can discard them without generating the pixels, right? You can discard that before. Does it sound reasonable for you? Okay, so because each triangle generates pixels, right? But if a triangle you see, let's say like this portion of the surface, right, whose normal points on the other side respect my point of view, like this, right? I will never go this one, right? And we'll never see this one, right? Because actually it should be, if the object is closed, it should be occluded by some other portion of the surface. So that I can discard directly the face, and even don't generate any fragment of pixel in the sequent step of the pipeline. So we have seen also how, I mean, given a triangle, right, then you have to illuminate a pixel, but what happens, like if you have multiple triangles from the same point of view, right, you have several triangles that project to the same pixels, right, which is possible because you can have object in front of you and object backward, right, and then essentially when you're going to project on the screen, they will going to hit the same fragments, the same pixels. So the strategy is like to use the Z buffer, which is a buffer where you actually store the depth for each pixel, right, generated by each triangle, and those are interpolated given the depth of each vertex, right? If you have a triangle, you have the depth of each vertex, you can extrapolate the depth of each pixel generated by that triangle. And in this case, you just have to overlap the mask and take the one that has the lowest depth. That's the one who won. Okay, I showed that last time. Okay, so we have two actually stage where we can actually program the GPU. There is another shader which is called a geometry shader. I don't go into detail on that. It's a bit more complicated, but it's cool. It allows, so far the pipeline now, it's like, okay, I give you some vertex, I give you some primitives, right, connecting those vertex, and then I can compute parallel operation on the vertex, right, here, right? I can move it, I can translate it on parallel, on the GPU, right, directly on the GPU. Then I generate the pixel, right, and I can write one program for each pixel to change the illumination, to change the effect of whatever I want. Small program running parallel for each pixel called also fragment, which is called fragment shader. Consider that there is another stage of the shaders that I'm not going to treat here, which is called geometry shader, which allows you to generate geometry within the GPU. So it's even another level, right? Instead of, so far you're getting geometry from outside and you do something, right? What you can do there is like invoke the geometry shader to generate even other geometry, just for notion, for you to know that there is a geometry shader. Is it's kind of recent. I think they introduced it like 5 or 6 years ago. Okay, so the thing is like, here you can write a short program that runs in parallel for each vertex, while there you can write a short program that runs in parallel for each fragment, for each pixel. Now we see how this works. So, and keep in mind that they run in parallel, so, and everyone has its own environment, and if you want to access, for example, there is a possibility of access to the texture, for example, right? So the fragment, the program can access to the texture, which is essentially similar to when the CPU access to the memory, right? To read the value of a variable or something, right? But in this case, consider that the access are done in a random order because they run parallel, so you don't know which is the first one who read, which is the first one to write. So you need other like special instruction to synchronize when somebody wants to write on the texture and somebody else wants to read, for example. We don't go into that details, but if you guys had done some course on parallel computing, right, a synchronizational process, that's where these kind of things should be applied. Okay. So cool thing of shaders is like, okay, so I mean the graphics pipeline do something, right? Try to match realism and try to find a good compromise between realism and efficiency. It has to run real time, it has to be fast, but it also has to be stable, right? So I mean, graphics pipeline is designed to do that, right? So then, but if you can program it, right, and you can write your own shaders, you can get nice effects like those, nice rendering effects in real time. Those are in real time, okay? And for example, yeah, here there is some gallery. For example, here there is one demo that you can see on 3. Yeah, you can create some kind of fog or global illumination things or other kind of effects. So for example, here there is one demo. Yeah, has been done with the shaders that actually for each sphere it actually take the image below that and try to deform it and create this effect that you see here with these bubbles, right? So just to show you that it's possible to include shaders also in Three.js. Also, this is another effect. Yeah, you see, it's pretty cool. It's also moving. Yeah, actually, you can actually change the color in real time of the vertices and write your function that can be a function that mimic lava behavior, right? So what you can do is, if you know how it works, you can go there, copy the shader, right, and for example, put in your word map generation some lake of lava, right, or I don't know, something like that if you want. Yeah, here it's another example that you can also use it to create this water effect. Consider that this is not geometry, this is not a texture, it's like you change the illumination dynamically, right, with the procedure that mimics this the flow of the water, so it tries to create these effects, right, on the water, which is pretty nice and realistic. And if you will actually model this with geometry, right, it will take forever because you will need a lot of vertices and you will slow down the entire application, right? Especially if you want to simulate each vertex independent. So you write this small procedure, right? This your noise function, your like water function. If it's nice, okay, right? It doesn't have to be physically accurate, rather than you want to be physically plausible, right? And nice to see most of the times for real-time application. Okay, so how do you program shaders? So essentially, what you need, what there is a programming language, right? That GPU support, which is called GLSL, which stands for graphic library shading language. I think I always call it GLSL, but I don't remember what it stands for. But anyway, so it's similar to C, right? It's a very low-level programming language, and you can, for example, you can define function, right? And of course, you have to define a main, which is the main call as in C, right? You know that you define the main, then you have defined functions, and maybe you call the functions from the main. Okay, you have a set of predefined function. Okay, so means that you can use, for example, some normalization, a lot of functions that are relative to geometry, right? So, for example, normalize a vector, perform dot or cross product, sum a vector to a point, and stuff like that. Those are already implemented that you can use. It's a small library, right? Or vector matrix multiplication, for example. Parameters are passed by value. That means that you cannot actually, when you pass a variable to the shader from outside, for example, you want to tune, I don't know, for a water effect, the amount of waves or stuff like that, right? So you want to pass some value. These values are copied, right? You cannot like do the computation and modify that value. The only output of the modification that you can have on the whole pipeline are fragments, right? You do computation parallel in fragments and you get back the results on the fragment. You cannot give back a variable to the CPU, okay? And yeah, there are some flow controls, for example, the for loops, which is unrolled, right, on the GPU, so it becomes this is, I mean, the GPU is very somehow stupid with respect to the CPU, but it's very fast. And then you have predefined compiled directive as in C, right, if you want to compile part of the code or not. Okay. Anyway, and there are also some types, basic types. For example, you can define so this is a typed language, right? It's not like JavaScript that you just say var. So this is like C or C++. You have to specify the type of a variable, right? You have float, integer, and bool mostly. And then you have also, as I say, there are built-in things that are related to geometry, right, operations. So then you have vectors. So vectors, vec2, it's like a 2D vector. You have 3D vector, 4D vectors. Similarly to 3JS, where you have vector 3, right, or vector 4, okay? And then you have vector of float, vector of integers, and vector of booleans, which, I mean, usually you don't use that, but maybe it's possible. Then you have matrices, right? Remember that every transformation in the GPU is done by multiplying the point times a matrix, and the result times another matrix, and the result times another matrix. So you transform the point from world coordinates, from object coordinate to world coordinates to view coordinates and clip coordinates by multiplying by matrix. And we'll see now how it works. Then you have a sampler that allows you to access to the texture. So if you want to store something on a texture and use during the computation, that's a way you can do. Use a sampler. Okay? You can define also array in the computation. Okay, so to understand what is a shader, first of all, I mean, I will show very simple example, and I will show also some programming. But first of all, let's see what is the minimal vertex shader, right? So what the minimal vertex shader should do, in your opinion, when it arrives one vertex? Remember that we are in this pipeline model, right? So I mean, here we have actually the pixels, right? And the vertex shader is transformed. It's it's the program which is executed by for each vertex. So what you have to do, right? So what is the path of a vertex, right? Come on, guys. I told that multiple times. So what you do? You multiply by the model view matrix, right? Model matrix, view matrix, projection matrix, right? Is it clear? Because otherwise that's a problem, right? So 3D vertex transform to the reference frame of the camera, which transform to the clip coordinates, which transform to the pixels, right? Okay, so this means that you first multiply by the model matrix, by the view matrix, and by the projection matrix, right? So if you actually follow the lectures, I told them that like infinite amount of times. So what the minimal shaders do then? It actually take the vertex and transform it to clip coordinates, which is exactly what to do. So this is a small program running per vertex, right? And what it does, it's like it. So this is a built-in variable, right? So when you run this program for vertex, so this program, it gets the position of the vertex already, right? So you imagine that this is a small program which is in the GPU, right? And it arrives a vertex and it processes it, right? And what it produces is this one. It's called GL position, which is the final position in clip coordinates, right? Coordinates which are -1 to 1 and -1 to 1 to the screen view, and depth is the depth that you use in the Z buffer, okay? So what you have to do then, right? So exactly what we have seen. So this is the vertex shader that if you program it, do exactly what the GPU without any shaders does, right? So basic pipeline, vertex, position, it transformed, multiplied by the model matrix and the view matrix, and here usually it maintained in a single variable, which is called model view matrix, which is then the multiplication of the two, right? So then you get the vertex and you multiply by this matrix, and then at the end you multiply by the projection matrix, right? And you're actually doing that. You are actually implementing this pipeline. So I hope you understand this way, because otherwise I don't know how to explain, right? You are actually doing this way. You are taking this one, multiplying by the modeling matrix, this should be M, multiplying by the view matrix, that is called model view, their multiplication. And remember, like multiplying one vertex times a matrix and then multiplying by the other matrix is like multiply the vertex by the multiplication of the matrix, because matrix multiplication is associative, okay? So, and then in the end you multiply by the projection matrix, which encode if your view it's perspective or orthogonal, right? And in the end what you get these clip coordinates, right? Which is exactly what this unit running in parallel should return to this, right? That do the rasterization, right? And then it find which pixel to eliminate, and then run a fragment program for each illuminated pixel, right? Massively parallel, okay? So let's come back. So this is, this is what happened when you actually render something on the GPU on Three.js without defining any shaders, like just regular material. This always happens, right? Because if you don't have You cannot have the trackball, you cannot have anything, you cannot define a camera. This is what it is, right? This implements the first stage of the pipeline, matrix multiplication. So what is another interesting, what do you see here of strange? Why this P here? I mean, position is a, position it's like 3 floats, right? It's a vector of 3 floats, okay? So, but why I have to put 1 on the end here? Why it's a vector of 4 floats? Yeah, because exactly, because this is an affine transformation, is encoded by 4x4 matrix, so you have to transform this into homogeneous coordinates. So this is what the GPU does, and this is why I explained to you all the things. Now everything becomes real, right? You can try to understand what's happening. So you take a point which is like 3 float, and you add the 1 at the end, right? And you transform it. So and then you actually implementing actually this stage. So here it's correct, as you see. Here it's correct, right? I have the model view matrix, this one, this model matrix, which is multiplied by the view matrix. So and then in the first, this operation, right? It implement these 2 steps of the pipeline, right? And then what I have to do is like I have this projection matrix, and I have to multiply by the projection matrix. What you have to return is this variable GL position, which is the position that will go after in the rasterization, right? So every fragment, every vertex shader will expect that you return the position of the vertex after you processed it, right? Simple, nothing difficult, right? So multiplication of matrix return a single variable, which is the position of the vertex, okay? That you can change, but in this case it's just a simple transformation. Okay, so going on, yes, that's exactly what I was talking about, because then from here, right, you need a position in the screen space, right? So then the rasterizer can choose which pixel to eliminate or not, okay? So as we said, like, why we need vector 4? You remember, like, I explained, like, in the first lectures that what this matrix implement here, those are affine transformations. So, for example, in this case, they transform one reference frame to another, or they rotate a vertex, or they do this, or they do like a projection transformation. If you have a projection matrix, for example, that can be perspective or orthogonal. But they are all represented as 4x4 matrix, right? 4x4 matrix cannot be multiplied by a vector of length 3, because if you remember, when you do like vector matrix multiplication, right? I hope you already did that at linear algebra course or high school, because this is important. So you actually multiply this row by this column, then this row by this column. So then it's essentially that the number of rows, the number of columns of the matrix should be equal to the number of rows of the vector. Otherwise, you cannot do row column multiplication. So what happens is, like, then it's you use this trick, right? You put an 1 at the end, and you transform the point to homogeneous coordinates. And in the end, you have this matrix that encode your transformation, right? And usually, if you remember, this is always 0, 0, 0, 1. And in this part here, you have rotations or other kind of transformation. Here you have the translation, right? I already explained this in the second lecture. I hope you remember. But yeah, so this is why it's important, right? This is why I wanted to understand. This is why I did all this boring math lecture, right? Because it's actually, if you understand math or linear algebra, you can better understand what's happening within the GPU, which is exactly programming, right? Applied math, right? Okay, how you, if you remember, like this point is transformed into homogeneous coordinates, which means add a 1 at the end because it's a point. If it would be a vector, it would add 0. So I hope you remember the difference. Points are positioned in space, while vectors are associated to differential quantities like velocity, like acceleration and stuff like that. Essentially, internally can be the same kind of representation, tree float, but the meanings is a bit different, right? Okay, and then you have like fragment color, fragment processing, fragment shader. And what you have to do in fragment shader is return the color, final pixel color, right? So I will show you later some more sophisticated shaders when I will show the programming. But the thing here is like, for example, this shader, for each vertex that it's past the first stage and is transformed, you just return one color, which is R, right? So this is the other built-in variable of the shaders, of the fragment shader, that the fragment shader should return, right? So this color actually, it's the color that you see on the screen, okay, that you can program it, how to get it, okay? Okay, so these are the basic one. Then we'll see, I will do some exercise on Three.js to see how to handle that. So keep in mind that there is another set of operation that you can perform on the shaders. Just for information, because if you want going to program shaders, you have to know that, right? It's not required from the exam, right, from the project, because this is a bit difficult, tricky, and I know that shaders can be a lot time consuming when you don't know how to properly code. So I kept this simple for this year, but will be in the exam, in the quiz. So it's better if you know that you can do a set of operation, for example, on vector tree and on scalars, right? You can add the sum, you can do product point-wise component for each component of the vector. So you take two vectors and to do like x times x, y times y, z times z. You can do like dot product and cross product. If you remember basically what are the operations, if I have a point and I sum a vector, I'm actually translating this point to a certain quantity to another position. Okay? Easy. I sum a vector directed along x to a point, so I'm moving this point along x. Nothing difficult. Subtraction, then given 2 points, I get the vector that connects these 2 points. Okay? Okay. Yes, indeed, if I have point plus vector, right, what I obtain is translation, right? So for example, I have this object in this reference frame, I add this vector, and then I translate it. Yeah. Multiplying a vector by a scalar, and do the scaling, right? So we already seen that thing, just to refresh a bit. And of course, you remember what is dot product, right? When we use a dot product, remember when I said like angle between vectors, where I use dot product cosine law, where I use the cosine law. You remember? Nobody remember? Sorry? I don't understand. No, speak louder. Projection, no. No, projection, no. Projection is I multiply vector by matrix, right? So where I use dot product? Come on. Illumination, right? So the direction of the normal times the dot product between the normals at the point of view. So getting which pixel get more lights than others, right? Okay. So you remember that about illumination? You also did the quiz. I hope you didn't do randomly, but you actually studied the slides, because otherwise it means nothing to you, right? So you remember that what are the points that gets more lights in the surface? So who can answer? Come on. So I have the surface, I have a lighting, right? How I can calculate which vertex get more lighting, get more light on? And for each point I have the normal, right, on the surface. So nobody answered that? I mean, it was in the quiz. So do you think, so if I put a light here, right, will this point get more light like this, or will get more light if I put like this way in front? Yeah, of course. Then what I have to see? The angle between the normal on the surface and the incoming light, okay? It's called a diffuse component. And I explained that during the illumination, right? A lecture. And what I use dot product, which is exactly these things that you have here in the shaders, right? Dot, okay? Which tells you how much two vectors are aligned. Dot product of two coincident vertices, two coincident vectors are 1. Dot products become 0 when they are orthogonal, it becomes less than 0 when they are opposite, right? Simple. I explained that multiple times. I explained the lighting multiple times, and I show multiple examples. It was also in the quiz, right? And you will see now what happened. And cross product, where I use cross product. Yes, exactly, to compute the normals on the mesh, right? So it's actually I have to take two vectors. Given two vectors, the dot product returns always the vectors which is orthogonal to the plane where these two vectors are defined, right? So given A and B, I actually, if I do cross product, I get this. So do you guys had some linear algebra exam on before now? Like, did you have a no linear algebra exam? Okay, and okay, that's bad. Because that's very important. Yeah, in general, and then you have also this cross product, right? Which is exactly what I'm trying to explain you now. Okay. So then you have some kind of operations. For example, get the length like the norm of a vector, get the or taking a vector and normalize to get it unitary length, because a vector can be like length 10, right? If I want just to get directions, I want to normalize it, right? So I just make it of length 1. Okay, so coming back to the shaders, we have three kind of parameters on the shaders. We have attributes, uniform, and varying, okay? So this is tricky. So attribute are some variables that you can specify from your program, right? And you pass to the shaders, which may be different for each vertex. So it's a variable that you specify for each vertex, like a parameters that you want your shader doing something given a parameters. That's the way you set the parameters for the vertex shaders, right? Then you have uniform, which are, so consider that these are can be only used in the vertex shaders, because these are for vertex, right? Because then in the other one you use you perform operation on fragment. Here you perform operation on vertex. Then you have uniform, which are other variables, read only again, that change for each phase, right? You can set one variable for each phase. and that can be accessed both to fragment and vertex shaders. And then you have varying, right? Varying are some of sort of variables that you can define to exchange values between the fragment, between the vertex shaders and the fragment shaders. So, for example, again, let's say like you define in the fragment shaders, in the vertex shaders, one color for each vertex. So in the fragment shader, when the triangle will arrive and illuminate all these vertices, right? For each pixel of the triangle, you will have the linear interpolation of this color between the color of the vertices. And here is how it works. So let me see. Yeah, we'll see later. So this is a way to exchange, for example, color information. For example, you can specify color of a vertex, right, and specify somehow. And once you go in the fragment shader, this vertex, you will have the same vertex, the same color for each fragment. So in this sense, for example, if you have something like this, let's coming back to our example, right? So yeah, suppose you have something like this, right? Here, how many vertex shader you have for this one? How many vertex shader there will be?
One.
No, 3, right? You have 3 vertex. 3 vertex, right? And how many fragments? Like 1 for each illuminated pixel, right? So, and if you define the color here, suppose you define the color here, here, and here. So the fragments will get, if you get a varying, right? Suppose this is blue, this is red, and this is green, right? So this value here in between, there will be interpolated by the GPU, right? And you will get here some color like varying between R, G, and B, right? And then in the fragment shaders, each of these pixels will have its own color, which will be the interpolation of the color that you pass to the vertex, okay? It's okay? Okay. So, like, imagine like you have 3 small programs running here, here, and here. So each one set a color of the vertex. Here is set the color red, green, and blue, right? So then you process this one, and after you get a set of fragment shaders, each one running on each one of these pixels, okay? And they will get the varying, which is the class of variables that is interpolated, right? And the varying will be the value of each of the varying will small fragment shader, which is a program running in parallel for each pixel, will get is the interpolation of the value of the vertices, right? We'll see how interpolate means. Okay, so you will have this. Coming back to our situation, you have these varyings, which allows you to exchange values from the vertex to the fragment shader, right? And the output is GL position for the fragment, which is the position of the vertex in clip coordinates, and the color of the fragment for the fragment shader. Optionally, you can also change the depth. Depth you use it in Z buffer algorithm, right? You remember, like to find which one is in front with respect to the other, okay? Okay, so we have, yeah, here is like a main overview about the thing. So we have attributes on the vertex, right? Then in the shader we do computation on the attributes on the vertex, and you generate the varying, which varies for each illuminated pixel within the phase, okay? Here they are interpolated during the rasterizer, so when you decide which pixel illuminated, and then you have a small program called fragment shaders that takes this varying and do other computation and eventually like create a color in output, okay? What does interpolation mean, and how we interpolate values from extremes, right? So you actually here there's a bit of terminology. So if you have three constants scalar, right, and you combine like them, you multiply each values and you sum up, you say like D is a linear combination of these points, right? Otherwise you can say that this interpolation, if all these values like are less than 0, sorry, less than 1, actually no, they sum up to 1 and they're bigger than 0, and otherwise you have extrapolation, right? So in the other sense you have to try to find the weight, okay? I mean, if at least 1 is less than 0, then it's extrapolation. So, but it's just a terminology. The important concept is like that. Okay, so given the fact that interpolation, suppose you have this weight, right, that can vary between 0 and 1, okay? So how you define, for example, all the point that stays on the line, right? The point that belongs to a line is the region of the point that can be interpolated by the two constant, by the two extremes of the lines, right? And interpolated means both are positive and both they sum up to 1. So for example, this is 1 v0 plus 0 v2. So what will happen to a vertex, let's say like here? Which weight you will put? Come on. No answer, really? I mean, how you will interpolate a point here? Here, in the middle. What is the middle? Yeah. Yeah, of course. Come on. Half, right? Average. 0.51 time plus 0.5 the others. Okay? This one is the opposite. This one is, for example, 0.75 v1 plus 0.25 v2 and so on. And this is exactly what I say, right? So I don't know if sometimes you don't answer because you think it's too easy or you don't understand. I'm scary about that because, I mean, getting 2 points, how to find the point in the middle, right? That's, I don't know, super easy, right? Sum up and divide by 2. I mean, average, something that you study, I don't know. It should be super easy. So, and this is exactly what we are doing, like multiplying 2 points by 0.5, it's doing the average, getting something in the middle, okay? Okay, so, I mean, varying, so that here the thing is like if you vary these two actually constant, right? You're actually interpolating, you are actually expressing all the points within the line. And similarly, you can do the same for triangle, right? And you actually, what you use is called barycentric coordinates that I already explained it. And if you have 3 points, let's say like in 2D space or in 3D space, you can actually, in 3D space, for example, which is the space that we are using, a triangle is the set of points such that you can express this point as a linear combination of its vertices. Instead of in a line there was 2, right? In a triangle there are 3, but it's the same thing, right? You have 3 scalar, right, that sum up to 1. So for example, now what would be the coordinates, barycentric coordinates for a point in the middle here, right? Yeah, 0.3, 0.3, 0. I mean 1 over 3, 1 over 3, 1 over 3, right? And then you get like the barycenter of this triangle, right? So during doing this game, then you can actually express this position, right, as a linear combination of the vertex, this position at this one, right, and this position, which is the center of mass, it's 0.3 periodic, right? I approximated 0.33. Yeah, and for example, if something is on the edge, right, this is it boils down to line interpolation, so means it's 0.5 v1 and 0.5 v2, right, and so on. If you get this one, it's much closer to v1, so you have 0.7065 and so on. Okay. So then, given 3 points that sum up to 1, the given 3 weights that sum up to 1, okay, and they are bigger than 0 also, and less than 1, then the x is a point on the triangle if these 3 are positive and they sum up to 1. So all the points inside the triangle can be expressed as a linear combination of its vertex, and this linear combination is given by values whose are bigger than 0, less than 1, right? And they sum up to 1. If you variate all this possible configuration, you actually do all the points in the triangle. And why this is important? Because barycentric coordinates are used to interpolate values, right? For example, if I have here red, blue and green, so the color here would be more blue, would be more red or green, in your opinion? I mean, blue, red, green. 1 point here, more blue, right? And 1 point here would be like red, right, and green. So, and how I do that, right, is exactly this concept, right? So, this is the blue, right? This is the green. This is the red and the green, right? So I derive this weight, and then I do an average between the colors by using 0.65 for the blue and other 2 factors for the 2 other colors. So that doesn't mean that if you have a point like moving on the triangle smoothly on the surface of the triangle, so I will be able to smoothly pass from one color to another, which is exactly how we interpolate values on the GPU. Okay? Barycentric coordinates, interpolation. Okay, so this is a bit of physical interpretation of barycentric coordinates. It's the center of mass if you have some weights attached to the vertices, right? When it's 0.3, 0.3, 0.3, it's the middle, right? If you go and you put some other weights on other vertex, the center of mass will change, but will stay within the surface of the triangle. Okay. Yes, then actually what I said before is like the rasterization, it takes the vertices and then interpolate using barycentric coordinates, for example the color, right, within this varying, right? If you do Gouraud shading, for example, you interpolate the color, right? If you do Funk shading, you interpolate the normal, right? But you interpolate the same way using barycentric coordinates, and this is done by the rasterizer, okay? And the fragment stay there, and it arrive already interpolated. The fragment it's lazy in this sense. Okay. Yeah, here it's another kind of interpretation, more geometric, but I think it's difficult to say. Okay, so then, let's see some simple shading, and then I will show you coding. Okay, so we have seen, like, every time you specify a vertex shader, you have to specify a fragment shaders, right? They have to return GL position one and GL fragment color the other. For example, in this case, what you get, constant lighting, gray, right? The position is multiplied by is transformed, right? Model view, projection matrix, PAM, position. Rasterize this position and return me a color that here I don't use. I just illuminate, get each pixel of the rasterization and put it to gray, right? PAM, like that, boom, gray. what I can do is like do something better, right? I can take the normal from the vertex, right, and I can put in a varying. Then I actually, when I run the fragment shader, then I actually do, you remember, dot product between lighting direction and normal on the surface. The amount of illumination hitting a point on the surface. In this case, I do it per pixel, right, per fragment. So you remember what this lighting model, shading model is implementing this shader? We have only two, right? One, it was computing lighting for vertex and then interpolating the color, right? Here what we are doing. We are not doing so, right? We are interpolating the normal and then computing the lighting per pixel. So exactly, func shading, right? What I'm doing actually. So if you see the program, I mean, I don't want you to understand the instruction deeply, just to have an understanding about how the pipeline works, because this is important, right? So what I'm getting here is like it's like a built-in variable, right? So when you actually render something with normal, you remember you pass per vertex normal, right? Per vertex normal is this one. So when you pass per vertex normal, the little shader staying at the GPU, you get the normal from the CPU, right? Get the normal, and then you actually do the same kind of transformations like before for the vertex, right? For the position, but you do one other thing. You define a varying, right? And then you specify the normal for each point or extreme of the triangle, right? And then this normal will be interpolated here in between. You have a normal here, you have a normal here, you have a normal here, right? Then will be interpolated within each pixel, right? And then each fragment will have a different normal, which is the linear interpolation between those, using barycentric coordinates. You don't have to do so. GPU does the interpolation. But then, when you actually have the normal, right, which is the varying, right, this will be interpolated per pixel. So what you have to do is you have to compute the level of gray, let's say like is illumination, right? So the gray level of the color that I will put out in the fragment color as a dot product between the direction of incoming light that here I hard-coded, but you can get also from outside, from the shader, okay? And the normal interpolated per pixel, remember, right? So if you zoom in, the triangle has more pixel, then you compute it more. So it's not, I mean, if you have a triangle, right, it's small on the screen, so it activates some fragment shader, right? When it becomes closer, it activates more shaders, right? It's always infinitely smooth. So that's why it's important, shaders, because you can do operation to the precision of the pixels of your screen, not the precision of the geometry that you have, right? Yes, that is func shading. I think I go on because I think you remember, right? It's exactly like that, right? Now it's more clear what's happening, right? I mean, of course, it takes a bit of time to understand what the shader, like programming like a shader, right? But it's important to actually understand the concept behind that. Okay, so this is again the difference between per vertex lighting or per fragment lighting, right? You get better result, but it's a bit more expensive because the shader has to do one dot product, right? Instead of just interpolating the color coming from the vertex. The fragment shader has to do one dot product. Yeah, exactly like that, right? So you have the normal, and then you do dot product of the normal with respect to the light direction, and then you get your final effect, okay? You can actually have other cool effect on the shaders, right? So for example, you can have this kind of strange cartoonish illumination. We'll see the code now, how to do so. We can have, so what you can do, what I usually do is like, I go in MeshLab, for example, and there are shaders that you can copy. For example, let's say like I run MeshLab, right? And then I don't know, this one. Okay, I have this mesh. Then I can render shaders toon, right? And I have this shader, right? If I put per vertex shading is much, and this is kind of cartoonish, right? If you want to copy the fragment shader and the vertex shader, you have to go here. This is the vertex shader, main, very simple. This is the fragment shader, right? Small programs, and then here you have the parameters like uniform, right? That you can set here from the interface and change the parameters, right? And then you can copy this thing, right? Copy paste on your code if you want to get these effects. Not all this set of instructions that runs on Three.js but there are others. Like a couple of instructions has to be standardized to run also on the device, like the phones. And this in general you can see a lot of shaders, right? You can also program your one if you are good enough. So you can have this kind of other effects like gold or stuff like that. So how do we do in Three.js? So you have to generate a script with a name. You name it your ID, vertex and fragment shaders. Then you write your main. It can be also like a different script on a separate file that you include. And then what actually, so far we have seen Phong, Lambert, basic material, right? We have also shader material, right? Shader material is this advanced material for cool guys like you guys are, because now you are doing very advanced things on graphics. This is very recent thing, and this is something that you can spend if you go to work on a big company, graphics company, right? There is not so many people that know how to do shaders because it's difficult. So if you are interested in going more in detail on that, we can work together. And then you have to actually define the vertex shader and the fragment shader for the material, right? And the way to define it's like you define you call this function get element by the text content, take this content and it loads, right? And then you define your vertex and fragment shader for this material, and then straight like before, you just associate the material to the object, and that's it, okay? And then you can actually, for example, define some attribute. For example, let's say like I want to define like this one, which defined per vertex, right? You remember I can define an attribute. We'll see later in the code. Attributes are defined per vertex, right? So I should be able to pass a different value for each vertex, and the way I do it's simply the way I do is simply like this way, right? I create a float 32 array. So this is a float and this kind of format that can be digested by the GPU, right? Then you set up, for example, the displacement, right? And then you say add attribute vertex displacement equals to this one, right? And then here is specified the number of floats for each one of the attribute. It can be like 1 if it's a float, can be like 3 if it's a vector 3, right? Depends on how you encode it. Anyway, okay, before to go on and to show you some code, right, that you can use, that you can you have to be aware how. There is another thing that you should be aware of. It's what is called GPU, right? General purpose GPU. So there is a huge research line on that. So what happened is that somehow the people realized that oh look, we have a like a great computational power in our GPU processing unit, and we are not using. Computational power means to compute, to make calculations, right? And so the people start using GPU for doing massively parallel computation for some of the problems that can be solved in that. So the people that do like, for example, mining of Bitcoin using clusters of GPU, or you know about Bitcoins, right? And you can mine Bitcoins with that if you are smart enough to write in a very parallel manner, right? There is people who are doing like uh, protein folding, right? So when you have to try a drug, if it works or not in the cell, right? You have to see how this drug deforms, how it can attach the proteins and stuff like that, right? And then you actually, it's a very computational intensive problems, and then people is doing that also with the GPU, right? I mean, they realize that they have some very computational uh, important computational power with low price, so why don't use that, right? Because at the end it's going to be faster than the CPU for parallel computation. So then here there is some small demo about how you can use the GPU to do some kind of computation. For example, here it actually uh, modify the position of these birds, right? And then you can actually change the number of birds here, right? You can have more, and with your mouse you can actually disturb the birds, right? I mean, what is computed in GPU is the position of the birds, right? It's not the classical way that I've shown you before to do some graphical effects. Here is you're actually doing some simulation, right? You're using the GPU to do some physical simulation. In this case, it's crowd simulation, right? And maybe if you have to run this on the CPU, it will be, for sure, it will be much slower, right? But because the problem it can be parallelized, then it works. It's fast. Here there are other examples. For example, like this water, like you can change dynamically with the mouse the behavior of the water. So to simulate this fluid in real time, again, with the GPU in parallel, much faster, right? And then yeah. Yeah, and then that's it, right? Now I'll show a bit of programming. So just to recap, we have two small programs, one running per vertex, one running per fragment. The one running per vertex is called vertex shader, one running per fragment is called a fragment shader. So the minimal vertex shader is the one that take the position of the vertex, transform by multiplying to the model, to the view matrix, and to the projection matrix. Actually, the three stages of the pipeline that generate the clip coordinates, right? This is what actually the GPU basically do all the time that you render something, right? It does implement this shader, right? You can write, it will do the same, okay? And then you return the position, and in the end, in the fragment, you have to return the pixel, the final pixel color. We have three kinds of attributes, and we'll see now how we'll use that. And attributes are interpolated between vertex and fragment shaders using barycentric coordinates, which is exactly this kind of concept that you can express each point on a triangle as a linear interpolation of its vertex. So then you can also interpolate quantities from vertex inside the triangle. And we have seen also how to include shaders in HTML and in Three.js. Now I'm going to show you a bit of magic with shaders. And okay. So I actually already coded that thing. So maybe it's here. No. Okay, initial setup. Okay, initial setup. Let me forget about all this shader. We'll see step by step what I'm using, right? Let's start from so these are all shaders. You see, like here it's like I define my vertex shader, I define my vertex shader, and I write my main here, right? So when I have to use it, what I do is like actually have to associate the vertex and the fragment shader. So this is a basic problem, as you probably did so many times. Define the scene, define the camera, then define the renderer, then resize function, you add the camera light, you add the camera to the scene, ambient light, object, you load the bunny, right? You load one mesh, then you set the material and you set the material to gray, Lambert material, right? Straight. Then we'll try to add shaders. And then what happens is that, okay, simple, right? So let's try, so this is what we have done so far, right? Load the mesh, visualize, Lambert material, you can put Phong material, if you want translucent, that's it. Okay, so let's try to modify and to define by myself the shaders, right? So let's comment this one, right? And I have step-by-step things to show you. So here I define this shader material, right? Which is a material that on that I can implement my shaders, and then I set the shaders I want to use, right? So I can set my fragment shaders and my vertex shaders. So, and the idea is like here I actually get this name, right? And then let's see what happened with this vertex shader simple, right? Vertex shader simple is a simple vertex shader that implement what I'm actually doing, right? It takes the position of the vertex, right? And then it multiplies by the model view projection matrix, the one that we have seen till now, right, in the lecture. And then you multiply by the projection matrix, and you get the position back. Additionally, interpolate also the normal, but we are not using so far. I will see later. Okay? And then I have the fragment shaders, uniform, right? Which actually is a stupid fragment shader that it returns me only like a uniform color of gray, right? What do you expect to see then, right? Rather than gray, right? And indeed, it is like that, right? So I actually transformed my vertex to 3D, and then in the end I associated gray to all of them. That's the result, okay? So what happens if I actually try to do something more complicated, right? So let's say like I actually do another shader material, right? And I use the same vertex shader, but then in this case I implement Phong shading, right? I implement Phong shading in this way. As we see before, I take the normal interpolated from the vertices, which is V normal, right? It arrives from the vertex shader interpolated for each fragment, and then I multiply by position of the light, right? And then I get the color gray that I want to render, right? So depending how much the direction of the light is conform to the direction of the normal, I have more light and less. What happened is this. Let me save it. I use these other shaders, and then I get, wow, Phong shading, right? Of course, I mean the light is fixed, right? If I move, the light is always in the same position, okay? I will show you actually how to move the light also in the shaders. Okay. Okay. Now, let's go on. And we have next step, right? Let's see another shader, right? Where I actually for example, I set a value, right? So if you want to pass a value to the vertex shader, you have to do like uniform, right? You set the name of your variable, you set the value, right? And you pass to the uniform of your program, right? So then what happens in the vertex shader, right? You will exactly have this value delta, okay? What I'm doing here is I'm like perturbing the geometry, because the vertex shader, what can do, it's like modifying the position of the vertices, right? So, and I'm moving the vertices towards their normal. So then what happens is like, so you see, like I get position plus normal times delta, right? So normal is a vector, I sum the position plus a vector weighted by this, and I'm moving each vertex toward this normal. So what I get, if I save, what I get nothing, really. Yeah, too much. What I get a fat bunny, right? I get a fat bunny. What I did, I actually simply like transformed each vertex toward its normal. And so the bunny is inflated, okay? And actually I don't do this on the CPU. I do this on the GPU, right? For each vertex in parallel, right? Okay? And this is exactly what this vertex shader doing, right? What this vertex shader doing is like taking the position and summing the normal times like some the amount of displacement you have to do, right? So it's moving along the normal on the surface, it's essentially inflating it. Okay, but I can do even something more complicated. For example, I can actually let me uncomment this. I can actually set a displacement different for each vertex, right? Instead of the same. Okay? What I have to do is, because you remember attributes, you can set different attributes for each vertex, right? So what I do is like exactly these things. I create an array, the same number of vertices of the geometry, right? You maybe already know about this code, you have seen several times, right? And you actually get and you set this value, right, as here it's a sine function, but you can set whatever you want. So the thing is like you can create these vectors of attributes, right, and then pass to the shader, right? And then you have this shader here that will get this vertex displacement, right, which is different for each vertex, right? And you have the delta again, right, which is uniform. And this vertex displacement, it's set up here, right? And you set here when you add attribute to the shaders, and you pass the kind of attribute, buffer attribute, right? A vector, one different for each vertex, right? So in this case, what I'm doing, I'm trying to perturb differently for each vertex, and then I get something like this, right? You see, like a sine function along the y, okay? Yeah, I mean, it's just to show you basic stuff, okay? This is done, this deformation is computed on the GPU, okay? Now, let's try to do another thing. and yeah, just to show you the different possibilities, and I can put this code online afterwards. You will have the video also of this. Sorry, let me comment out. Now you have step 5, which is, in this case, I try to I use the regular vertex shader that inflate the bunny, right? But then I use another fragment shader, which actually, instead of getting the color, right, normal, it combine the color with the normal, right? So the normal is used as a color itself, plus the shading. So what you get is this. Maybe you can go into what you get is this, right? So here the normal is represented as a vector. It can be represented as a color, RGB, right? And then instead of just returning the gray, you return in the gray times, so the gray is actually the RGB, which is the X, Y, and Z of the normal, and then because it's between -1 and 1, you have to bring between 0 and 1, so you divide it by 2 and you sum up 0.5. Okay, so this is a way how you can change colors in the fragment in some meaningful way. Finally, you can do even something more complicated. For example, I actually get this I also, for example, here I transform also the light position and the normal with respect to the orientation. So now this is, you see, like if I rotate, it's completely dark because light is fixed, but also the normal. So in this case it's not, right? What I did, I actually, instead of changing lighting position, as you actually do when you put the light in front of the camera, I did another trick. I actually sorry, it's not that. What I changed is the vertex shader, right? What I changed is like I change the normal on the surface, right? I change the normal of the surface and I transform the normal of the surface with respect to the viewpoint, right? So instead, yes, I mean it's a bit of an hack, but it works. So instead of transforming the lighting, you transform the normal and you multiply by the current rotation that you have from the point of view. And to do so, you have to multiply by this normal matrix, which is essentially like the same model view matrix, but instead of being 4x4, it's the 3x3 upper part. Because normal is a vector, it doesn't need any translation and anything, so you just need rotation, right? You can get the upper 3x3 part of the matrix, and that's it. I mean, normal matrix is that part. It's just a shortcut to get the upper left part of the model view matrix. Okay, and I mean, I think you like that. I did a lot of effort to trying to show you different example how to use that. Again, this is not gonna be required on the project, but it doesn't mean that it's not interesting, right? And there is another shader that I actually did, which is this one, right? I copied from MeshLab. This is a bit more complicated, but it's the same kind of vertex shader that transform like normals on the surface as a hack to transform lighting, transform the vertices, right? And then you have this shader tool that you can use also for your code, or you can go and copy some other shaders that you find on the web, right? You can just copy paste, right? I mean, if you understand what happened and can try to tune the things, it's better, right? And that's it. That's it for now.